I will be presenting a paper titled Industry Scale IR-based Bug Localization, a Perspective from Facebook. Let's start with what IR or Information Retrieval Based Bug Localization is about. IR-based methods cast bug localization as a search problem, where the search query is some evidence of a bug such as a bug report, and the documents to be retrieved are code entities such as files in a repository. In this work, we have identified several key criteria that an IR-based bug localization method must satisfy in order to be deployed at Facebook scale. First, the method must isolate to commits. This is because a single file can be owned by multiple developers and teams and can have multiple changes in a short time frame. The job of on-call engineers in the company is to attribute a bug to the right developer or team, and this can only be done by identifying the commit that caused the bug, not by using the location where the bug is present. Secondly, the method must be unsupervised. At Facebook, developers are incentivized to fix bugs as soon as possible, and so a lot of data exists on bug fixes, but they don't have a necessity to find the blame commit that introduced the bug, and so not much data exists on the causes of bugs. Third, the method must handle complex queries and documents. We will take a look at what this means, but in short, a query or document contains various features from different sources in our setting, which are typically not considered in other IR-based methods. Finally, the method must also understand the semantics of features. This is because Facebook's codebase is heterogeneous. There are multiple programming languages and coding conventions in different parts of the codebase. For example, developers might use IG in place of Instagram, and simple word relevance-based methods wouldn't be able to capture their synonymous nature. From our characterization of IR-based methods, at least one or more of these constraints are not satisfied by existing methods, which motivated us to design bug-to-commit, our contribution to IR-based methods that addresses these constraints. Let's now take a look at what role bug-to-commit plays in Facebook's software development workflow. Developers at Facebook write code and push it to a commit queue, which is handled by a continuous integration system. At regular intervals, the commits in the queue are bundled together into a batch or a build, which is then subjected to end-to-end tests. Once the tests are complete, server-side code is pushed onto Facebook's fleet, and client-side code is bundled into a release and sent to app stores. Bugs could be detected at both stages, either in the end-to-end tests before deployment or post-deployment. In both cases, a bug report is created by dumping various signals that could be associated with a bug, such as the stack trace and other metadata. For end-to-end tests, a bisect operation is triggered on the build and the culprit commit is reverted. For post-deployment bugs, an on-call engineer manually attributes the bug to the right developer or team to put out a fix. These two processes could consume significant amount of resources or human time, and this is where bug-to-commit plays a role in automatically identifying the right culprit commit for reverting or attribution. Why is this a difficult problem in our setting? Let's take a look at what could appear in bug reports and code commits. Bug reports could contain the stack trace obtained at the time of the crash, the exception message associated with the stack trace, metadata about the environment in which the crash occurred, such as the surface the user was in, like profile or newsfeed, the metric that's regression in performance, such as the name of a function or a performance test, snapshots of traces in machines where the regression was detected, and the description in a task tracker if one was filed for the bug. Similarly, on the document side, code commits could contain the developer written title and summary of the change, a series of commands called the test plan that will validate the changes, names of files that are modified in the commit, name of the server-side config that was changed, and finally, snapshots of stack traces of functions that reference the code change in production. Essentially, what this says is that a query or a document in our setting is not a monolithic bag of words that IR methods typically consider as a query or a document. Let's take a look at a more concrete example of a real query and document shown here after some obfuscation. Immediately you would notice that the query is actually more complex than the document itself, something that is atypical for IR methods. Also, the query contains multiple features such as the metric and regressing traces. Each feature also has its own characteristic. For example, the metric name is short and pithy, whereas the traces are long and noisy. In this case, the word tag is highlighted because in truth, it is the most important and relevant word to match this bug report with the right commit. However, if we take the metric name as our query because it appears to be succinct, we would be led to believe that the word photo might be very relevant. On the other hand, if we consider the entire bug report as a bag of words, the word eval might appear to be more important. Adding to the complexity in our setting, developers sometimes used coalesced words in our code base that are somewhat readable by humans but often confuse IR methods that typically split by camel or a snake case. Moreover, even if the right word could be extracted, some words appear in synonymous forms, such as the word taggy here, which would defeat a stemmer or lemmatizer in associating it with the word tag. This is an example of a complex query and document with semantic overlap that makes it hard for traditional IR-based methods and that bug to commit is specifically designed to handle. How does bug to commit work? It is at the end of the day an IR-based method that uses vector space model. So as usual, it vectorizes the query and document into a high dimensional space using a vectorizer, and it ranks documents relevant to the query by using a similarity score in the vector space such as cosine similarity. Where bug to commit differs from other IR-based methods is as follows. To handle multiple complex features in the document as we saw before, it uses multiple vectorizers, one for each feature, each vectorizing the feature into a shared vector space. It also tweaks the vectorize operation to use a BM25 based encoding as opposed to TF-IDF that is normally used, and computes the vector for the document as the mean aggregate of the feature vectors. This ensures that the characteristics of each feature, such as word importances, are learned by the respective vectorizers independently during training. To handle the semantic similarity of words such as taggy and tag as we just saw, it trains a word embedding model, specifically word to vec, and uses the BM25 weighted word embedding for vectorization. It also performs a probabilistic parsing of words to not rely on camel or snake case based splitting. Finally, the query or bug report is also vectorized in a similar way, and the documents are ranked based on cosine similarity and returned back to the user. For the formalization behind these operations, we encourage you to refer to the paper. We evaluated bug to commit by running offline and online experiments on it at Facebook. We considered 3 applications of bug to commit: mobile crashes collected from the field from the Facebook Android app, performance regressions on the server side coming from Facebook's fleet, and the end-to-end simulation tests on mobile that are run before a release is rolled out. We also compared bug to commit with 2 related IR-based methods, Locus and Orca, in our experiments, and we found that bug to commit is able to perform more accurately in our setting compared to the other approaches. We also found that the word embeddings does provide benefit in terms of enabling bug to commit to match synonymous words, such as when a library is renamed or when developers use alternate spelling for identifiers, or the case of the words tag and taggy as we saw before. It also pushes the performance gain from bug to commit higher over the other 2 methods. Motivated by the offline results, we conducted online experiments on bug to commit's impact on Facebook's processes. Over a period of 6 months, we observed that bug to commit helped on-call engineers resolve 4 out of 7 so-called client-server regressions. These are rare but serious regressions that occur across client-server code bases and cause a lot of disruption to internal development. Bug to commit also helped on-calls in attributing server performance regressions by making them look through at most 10 candidates of likely culprit commits rather than hundreds. This reduced attribution time from typically 1 to 2 hours to just a few minutes, sometimes even taking the human out of the loop entirely if bug to commit was highly confident of a commit. It also helped the automated bisect system by enabling it to test the 10 most likely culprit commits immediately, reducing the median time from 9 hours to 3 hours, a significant reduction at Facebook scale. So, the final takeaway of our work is as follows. We put IR-based bug localization to the test in a large industrial setting like Facebook and found that it is definitely not a solved problem, as many practical challenges had to be considered. We designed bug to commit with the goal of addressing these practical challenges and push IR-based methods closer to industrial use. But there is still a long way to go in terms of getting widespread use of these methods. For example, considerations such as the interpretability of word embeddings may pose a challenge. In summary, from Facebook's perspective, while IR-based methods work well for most cases, they are not a silver bullet solution for industry scale bug localization.
Hello, everyone. Welcome to the session about fault localization. I'm Leonardo Mariani and will chair this session. I'm here with two of the authors, Vijay and Satish, who are happy to take your questions. You can write your questions on the chat. And while you think to your question, let me also remind that after this Q&A session, you will have the chance to join the authors in the breakout room if you want to interact directly with the authors. And of course, after this paper, we will enjoy another paper presentation. So I see we have a question in the chat by Tim. Can you say more about the use of bug to commit in the culprit finding application as part of continuous integration? And is the query the test log of the failing test? So please, Vijay.
Yeah, I'm just trying to read. Is the query the test log of the failing test? Yeah, so two parts to this question. So now bug to commit has been as said in the paper, like integrated with the continuous integration system. So as and when these kinds of bug reports or these symptoms of bugs are filed, the system is automatically triggered to help find the culprit commit. Is the query the test log of the failing test? Now, there are various different ways of symptoms of these bugs appearing. One of which is actually the failing test itself, and the actual query that is provided as this kind of document to the system would be, for example, stack traces that are captured when the test fails. This is one example of a symptom. And another example could be the name of the function that is regressing. For example, if the regression is in performance, then what is the name of the function that is regressing in performance, and what are the callers of those functions? So these are all the different signals that are captured and dumped as part of the query.
Okay, thank you. We have another question in the chat by Michael. Can you elaborate a bit more on the commit features you use? Does obtaining them involve any kind of program analysis, or do you use simply the commit as is?
Yeah, that's a very good question. So at our scale, we cannot afford to use program analysis on the commits themselves. So we basically treat them as textual features. So like said in the paper, we obtain the title of the commit, the summary, and also even the code changes. They are essentially treated as tokens. Now, one difference that one kind of slightly different way in which we capture the code changes is because if it is a code change, there is a question of whether a particular line of code was added or deleted, and those tokens are represented by a special character preceding that token, whether the token was added as part of the code change or it was deleted as part of the code change. But that doesn't involve any kind of program analysis. Okay.
I have maybe a related question. I see the bug to commit uses heterogeneous metadata in the analysis. Is there any kind of data that is like more relevant than other for the localization, or less relevant for the process, or is it everything equally useful based on your experience?
Yeah, in fact, everything is not equally useful. So that is the kind of the point of the model, trying to learn what are kind of the important parts. So what we've generally observed is that there are certain features, like, for example, large amounts of stack traces that are captured, and those features come with a lot of noise. And those, kind of the signal that is extracted from those features may be less important than a feature that is very closely related to the source of the bug. For example, the title of a function that's regressing. So of course, different features contribute differently to their own importances and relevance to the bug, and that is exactly what the model is trying to learn automatically, kind of from the data itself. So that's job of the training process.
Okay. There is a question by Peter. I imagine there is a lot of noise in your dataset. Do you compare failed test logs with normal test logs to reduce the noise in the dataset?
That is a very good point. So currently we don't do that. We don't do this kind of differential analysis of comparing a failed log with a normal execution log and kind of extracting the differences. I think one challenge to that would be to find out normal execution logs that are sort of in the same distribution as the failing log and not too different, and kind of making that comparison with them. That I can imagine that being one challenge. But having said that, that's definitely something that's worth pursuing in the future.
Okay. We have a question by Mikhail. Did you have a chance to compare your model to the models that try to localize bugs using the source code? While these models usually focus on finding the implicated file, they can be probably tuned to look for the implicated commit.
That is a good point. So we particularly picked for comparison the most closely related approaches, namely Orca and Locus, that localize directly to the commits. In our case, localizing to files directly is not particularly useful for like reasons explained in the paper. So we did not attempt that kind of a comparison. But there is a rich body of work on trying to localize to particular files or locations in the code base. And some of the challenges over there might be different compared to the challenges in localizing to commits, which come with all these kinds of other metadata that you don't often see in files. So that's one of the reasons we picked these two particular works to compare our works with, because they kind of address those challenges.
Okay, I see. While we wait for more questions, one quick question from my side. I see in the presentation you reported the results for the top 10 locations, if I'm correct. I wonder what happens if we focus on the top location or top 3. So if we focus on the very top places, how the results look like.
Yeah, that's a very good question. I think in the paper we reported top 1, top 5, and top 10 for various different applications. The top K makes a difference. So if you're particularly looking at just the top 1 accuracy, in one application where the top 1 was really high, we were able to kind of automatically attribute the bug to the right commit without having a human ever present in that loop. And this can be done with the help of the accuracy that you get from the model and also kind of a confidence that the model has in making that prediction. In other cases where the consumer of the information was not a human, but kind of like an automated bisect or automated test system, it's fine to go top 10 or maybe even top 20 or so, because the consumer is an automated system. So you're just spending some extra resources in trying to validate your result.
Okay. Good. We have a question by Tien. I think we need a quick answer because we have 1 minute now left. So it seems that you use word embedding, but it is still largely IR based. Is it right?
Yes. I mean, if I understand the question right, the end method that we are using is still IR based, right? It is based on casting this problem as a search problem from a candidate list of commits. So that end-to-end method is still IR based. Where we are using word embedding is to find out, is to represent the candidates and the bug reports in a vector space where we perform the search. And that is enabled by using this kind of word embedding model.
Okay, perfect. I think this is the end of the Q&A. So thanks to the authors for the video presentation and for answering the questions. Thanks to the audience. Now we have the breakout room if you want to interact directly with the authors. And also we have another paper presentation that is going to start soon, still in this session. Thanks for attending.